Hello, my name is Sujin Cho, and today I'm gonna talk about some things about carrier concentration. The first thing I'm gonna talk about is density of stage, and next thing I'm going to talk about is Fermi-Dirac distribution, which is here. And last thing I am going to talk about is about electron and hole distribution with energy. Uh, let's get it started. The first thing I'm going to talk about is density of state. And density of state. Before density, I said about that. Carriers are distributed for each energy state, as you know. And to know total carrier number, which means concentration, so integration as a function of energy is needed. So carrier distribution as a function of energy is needed. Understand? So these two things are what we needed to get about some total carrier number concentration. So first thing is available stage, which is function as a function of energy. And next thing is a probability of occupancy. Here, available stage, it is what I'm going to talk about as first. It is a density of stage, which can express simply by US. It means some locations that uh, how many locations are there to that carrier can available? And it is a function of some volume and energy. So density of stage is a function of numbers of carrier and of volume and of energy. In one dimension, first dimension, uh, we can get, we know that this wave, normal expression of wave function equal a times exponential jkx. And we let the period of the wave, one period to L, then wave function at zero and wave function at L equal, they are same, like a periodic boundary condition, and which can easily known as by easily known by these some uh, image. And for free electron, kinetic energy can express as total energy minus potential energy, and this equation cannot from here. This Kn means some uh, the Kn means this one, well, some available states, and it can express as 2 pi n over L because the period is L. So this delta K can express as 2 pi over L, and 1 over delta K can express as this one. But we should consider about some spin as a Pauli vector. So um, we should times 2. So number of stage per length per K, per length per K equals, we should divide this by uh, L. So we can get SK by this one. SK equal pi, 1 over pi. This SK actually means that, yeah, SK. this is some constant. So from to this equation as a kinetic energy, we can get about we can let this equation to change calculate about k. So this if we derivative this k by e energy, we can get this equation. So dk sk times dk equal se times de, and this se means function energy. So we can get these equations, and as this part means density of state, which is DOS, and this is a function of number of carrier over volume over energy. So we can summarize about this E by this equation, and this part is constant, and this we can know about that. This SE is different by 1 over root E. You can know SK at one dimension is 1 over pi. Next one I'm gonna talk about is second dimension things, and this wave function is about some second dimension, as you know, learned before, and express also can express like this one. And kx and ky have some discrete k because some integer nx and ny is some positive integer. So we can let some a number of stage per area in K or area in real space as this one. So equation can let this, and also we should consider about think about some spin. So times two. Actually, so difference of area in K space, and let like this one. We should know about this area, so this area can express that as this picture, okay, like this one, and it can express as this equation. So we should know about dA, which means very small value. So we should derivate it, and we can get this one. Sk dx, sk dx. Here's the we should get some SE. So SKDX can let expression like this one, and we know that this K is this one, and this DK and this K is this equation. So we put this in this equation, and we can get some SEDE, and we can finally get uh, density of stage in in second dimension by this one. But in this one, the energy is of some constant, so this is not a function of energy. Next thing I'm gonna talk about is third dimension. In third dimension, there is some kx, ky, kz. And in the same way, we should times two by this one. And volume of sphere, we learned this in some like a middle school as 4 over 3 times pi times k squared. And we should derivate it by this one, and we can get this equation, and skdx can skdk can express as skx ky kz and times this dvk. So we can get density of stage by as this equation. So and Here, first, this part is constant and this part is variable. So this is also one function of energy. We can get a graph of density of state over energy in 3 dimension in like this one, and 2 dimension like this one, and for 1 dimension like this one. And also can get a graph of 0 dimension like this. Next thing I'm gonna talk about the Fermi-Dirac distribution. The Fermi-Dirac distribution is some thing about some graph of energy by which that fermion particles then justify as fermion get like electron or hole. Um, so this equation is about Fermi-Dirac distribution for electron. Which means this F means Fermi-Dirac distribution, and this means energy, a function of energy. This seems may some hard work, but it's not that hard. Equal energy, which means main variable, and EF, which one is in here, means Fermi energy. But we can actually more say like Fermi level more frequently. And Fermi energy means that uh, possibility of existence of electron. The point that possibility of existence of electron became 50%, half percent, and KB, this is a constant, Boltzmann constant. Boltzmann constant means what joule of energy we can get at 1 Kelvin, and it has some this value, and he means temperature, which should express as Kelvin. So kVt means thermal energy, which can express as joule or electron voltage. This graph shows us that about some. It is hard to exist when energy is high. And this graph shows us about some. This general means uh, possibility of electron, existence of electron at 0 Kelvin, and this means possibility of uh, full electron at valence band, and this middle gap means intrinsic Fermi level, and it can also express as EM in this situation. EI means some especially expressed about Fermi level and intrinsic situation. Or if you some doping some stuffs and it may have different intrinsic different family level. And for whole, Fermi level of 4 can express as 1 minus Fermi level of electron, which can also express as this one. And this equation we get here, and if a Fermi level of electron is very big enough, and then you can ignore about 1, so we can get an equation of this by approximation. We have talked about some density of state and some energy work. Next thing, I just talk about the Fermi-Dirac distribution, so we can get some possibility of electron and hole. And next thing I'm gonna talk about is electron and hole distribution energy. To get this, we should multiply density of state and Fermi-Dirac distribution. This equation is concentration of electron equal density of state of electron times Fermi-Dirac distribution times electron. But it has some direct meaning only in conduction band. This PE means whole concentration of whole, and let we can express like this one. SE means density of state of whole and 1 minus FB, as we taught before. This is a Fermi-Dirac distribution of whole. So we can express as FPE. It has direct meaning only in balance band. This is a graph of some, yeah, this is an N-type semiconductor graph. And this part means Boltzmann tail by these equations. This area means total number of carrier over unit volume. So yes, we can mathematically think about this one. And this equation means, this N0 means concentration of electron at intrinsic situation. This means you should integration about to conduction band to infinity energy about density of state times uh, Fermi-Dirac distribution of electron. So we can also express like this one. Ne means that concentration at that uh, level, each level, and it's integral by energy. On the other hand, this way, also we can get about some concentration of whole when it's intrinsic. In 3D bulk, we can express like this one. And these parts are constant, so it is a function of energy. And we did these some works, mathematical works. And as you know, these works shows us about some relationship between carrier concentration and density of state and Fermi-Dirac distribution. From that section, which is n times p equal ni times ni. Mm, This EV minus C means some conduction band and a difference between conduction band and valence band. So we can express it as on energy band gap, and we can express here. And we can get intrinsic carrier concentration of root NC and V, small n C, small n V, exponential this one. This equation shows us that about if the temperature goes higher, and intrinsic carrier concentration also get higher. But energy gain back becomes larger, and then intrinsic carrier concentration reduce. For intrinsic semiconductor, N0 equal P0, and uh, EF means Fermi-Dirac distribution for intrinsic and Dirac distribution. So NC over NV can let about this one as we talked about before. And you can express like this one. So this can express as intrinsic Fermi level equal mm, this. This is about some mid gap, and this expression can let about here. And EI become larger or smaller as T. But because of room temperature, so EI should not be on big gap. And this part, we can get some intrinsic carrier concentration. Or we can write some NC and V as an intrinsic carrier concentration. So we can easily calculate. This partial equations means number of intrinsic semiconductor, number of electrons at intrinsic semiconductors equal intrinsic carrier concentration. And we can work about like this. From uh, conduction band to intrinsic carrier concentration. Intrinsic carrier concentration. Here is a number of hole in the intrinsic semiconductor equal intrinsic carrier concentration, which can express in here. And this is distance between intrinsic energy, from mid gap to valence band. So we can get an equation about NC and NV. So, and we already know about N0 and NP, equation like this one. And this equation shows us that about conduction band and difference between conduction band and Fermi level and valence band. So how much some dopants are doping? But with this one and this one, we can get equation like this one. So this equation shows us about uh, we can get some how many dopants are doping with intrinsic Fermi level and Fermi level difference. But this is quite different because as you see, both equations can let us know about how many dopants are doping in semiconductor. But this equation is by conduction band and Fermi level or valence band difference. And this equation is about some intrinsic Fermi level and Fermi level difference. And we can also get about these equations. We use these equations when we know about carrier concentration by some artifacts or stuff, and we know intrinsic carrier concentration, so um, we can know how far the parameter level is located from intrinsic value level. Finally, I'm gonna talk about for intrinsic semiconductor, we can use these equations. Like this means initial carrier concentration when the semiconductor is doping as n-type equal intrinsic carrier concentration plus free carrier by dopants. What if some free carrier by dopants is a lot way bigger than intrinsic carrier concentration? Then we can think about some initial carrier concentration when the semiconductor is doped as n-type equal intrinsic carrier concentration. It is same in p-type. And if semiconductor is doped by both donors and acceptors, yeah. So initial carrier concentration at n-type semiconductor can express as free carrier by dopants minus this one. In here, it is same. So free carrier by dopants are way a lot bigger than Na. Then we can think about that intrinsic carrier concentration equal uh, free carrier by dopant. This is all I have to. This is all I prepared, and thank you for watching my video.